Greeting everyone. Let's begin with the introduction to our project. Process scheduling is a key function of any operating system. It's responsible for deciding how the CPU is shared between multiple tasks. The main goal is to use the CPU efficiently and reduce waiting time for process. In this project, we focus on two important algorithms, which is FCFS, first come first serve, which run tasks in the order they arrive. SJF is shortest job first, which run the shortest task first. Our objective was to compare these two algorithms based on two key performance, waiting time and turnaround time.
The first algorithm used for the experiment for the project is the first come first serve. The first come first serve algorithm is the simplest non-preemptive CPU scheduling algorithm. It executes processes in the order as they arrive. Means that if they come first, they'll get the first serving for the processes, and it's easy to implement and ideal for learning. Um, it is the basic operating systems concepts. It also ensures fairness by preventing starvation, as every process eventually gets CPU time. In FCFS, which is the first come first serve algorithm, once a process starts execution, it runs until completion without interruption. It makes the algorithm straightforward and predictable. And despite the simplicity, FCSS can be inefficient when burst time vary significantly, which can be shown in the next um, um, next few slides as we present. So this is the code for the first come first served program, and for this, first initiate the user to enter the number of process. This is to know how many process we're gonna undergo, and then also print um, burst time for all the processes and ID for all the processes. Means that we can determine the ID for the each processes and then see which process come first, and then also um, um, change the burst time for all the processes to undergo the next scenario. The first scenario is the same burst time. For the next scenario is the different burst time. And then to calculate the waiting time for each process, we're using the calculations for the as shown just now, which is the waiting time. Initiate is the burst time, um, the burst time I minus one and the waiting time I minus one. So after this, we print the process ID, the burst time, the waiting time, and the turnaround time. Hi, my name is Zhong Shizu, and I will now present the result analysis for the first algorithms. In order to analyze different numbers of processes and different burst time effects on the FCFS algorithms time, average waiting times and turnaround time, we have to carry out different processes with both scenario. For the first scenario, we have used the same burst time, and then for the second scenario, we use different burst time. Each processes is increased by 2 until 10, and then carry out with same burst time and different burst times um, individually. As the processor increases, the executive order also increases. Thus, the waiting time has also increases. But the point is, we need to find out the difference as what is the length of the average waiting time in same burst time and also the different burst times. Throughout the experiment, we found out that using the same burst time is shorter, result in a shorter waiting time compared to a different burst time. The same scenario is carried out for egg processors. The number of the number of processors increased to 8 for these simulations, and we get the result as the average waiting time is increased to 10.5 units, while average turnaround times is also increased to 13.5 units. It's gradually increased compared to scenario B, which is in different burst time. It increased a lot as the average waiting time is increased to 14.5 units, while the average turnaround time is increased to 19.75 units. Last but not least, we have also done simulation with result for 10 processor. Again, we're using the sample time and different burst times for this experiment scenario. The first sample time is sample time. The average waiting time is increased to 9 units, while the average turnaround time is increased to 11.0 units. It is also increased gradually, but throughout the experiment, we found that the performance for the FCFS algorithm is performed in consistent and fair, and it's ideal for homogeneous workload. Although in different burst time, the average waiting time and turnaround time increase um, significantly compared to in same burst time, but it is relatively decrease or have small average waiting time compared to the another algorithms.
Hello, my name is Muhammad Zarfan bin Alkonso, and today I will present about the comparison of 4 to 10 processor in time burst. So now, for FCFS scheduling algorithm, so when increased number of processor from 4 to 10, we observed that when all the processors had the same burst time, the average waiting time and turnaround time increased linearly from 3 units to 4 processors to 9 units at the 10 processors, as you can see at the table here. And however, when the burst time differed, we saw the exponential growth. The average waiting time jumped to 33 units to 10%, clearly showing the convoy effect, where long job block shorter ones. So this highlight the scalability issue in of FCFS with varied workloads. So this is a data and graph for the process count versus the average waiting time. So this illustrating average waiting time the under FCFS, first come first serve. For same burst times, the line grows steadily, very predictably. You can see at the graph here. The line is for the different burst time. It's climb out, and the burst time it's linear. So So the curve is steepened significantly at 10 processes. So average waiting time triple compared to uniform scenario. So this show how even one early long process can drag system efficiency down in FCFS. So next it's the slide process is the process count versus the turnaround time. So the graph represents the turnaround time metric showing the similar pattern to waiting time but with constantly higher values. So in burst time scenario, it's predictable that the 5 units at the 4 processors at 11 at 10, but in mixed burst turnaround time goes for 10 to 44 units. That's a 340% increase, further proving the FCFS first come first serve struggles with non-uniform workloads. So here you can see the process count versus the burst time, where it's a same burst time. So it showed the establishment of metric all processors have identical 2 units burst time. So you can see at the graph here it's all identical and it's linear. For three line here, you can see the blue one it's execution time, and the average time it's the orange, and the green it's the average turnaround time. So here you can see the process count versus the different burst time, where the graph show the efficiency loss when the burst time vary, so revealing the substantial performance degraded ranging from 67% to 267%. So this analysis demonstrate how the burst time heterogeneity significantly amplified the convoy effect inherent in first come first serve scheduling. So you can see at the graph here, because of the different burst time, there is a curve at the three main parts here. You can see execution time for blue, and then green average turnaround time, and orange is the average waiting time. So you can see the same and the versus burst time in all process accounts. So the compare scenario here, different burst time across different counts with this same burst time, first come first serve performance. So very consistent in fair, but the mixed burst time, the longer jobs early in the queue hurt overall the performance. So you can see, for example, at the six processor, between the two data, so average turnaround time jumps from 7 to 18.67 at the different burst time. So unit when it's burst time, it's vary. So here you can see a theoretical calculation for FCFS, first come first serve. So we begin with the four processor burst, where it shows the burst time of 2, 4, 6, 8, and burst time in FCFS order. So this is the formula in FCFS order minus the arrival order. So this is the content P1 until P4, which is the content you can see 2, 4, 6, and 8. So this is here is the data for the waiting time. So P1 is 0 and it's equal to 0. So P2 0 plus 2, 2 plus 4, and 6, and so on. So for the calculation waiting time, total waiting time, it's plus all of this at the waiting time. So we plus all of this and it's equal to 20. So average waiting time, which is the answer of total waiting time minus the 4, because we use 4 processor. So we not minus, divide by 4. Because why we use 4, because it's a 4 processor unit. So and it's equal to 5 units, or 5.0 units. So here is the turnaround time. So turnaround time, it's equal to waiting time plus the plus with burst time. So you can see it's the data of the sheet here. So the turnaround time, the total turnaround time, we plus the turnaround time, same as the waiting average waiting time. And then what do we do when we got the value? We divided by 4, which is this is 4 because it's 4 processor, and we got it at the 10 units. So here it's for 6 processor. We use the same method as the fourth processor. You can see which average waiting time, uh, average turnaround time. So average waiting time, which is the plus for the waiting time at the table. So we plus all of them, and then we divided by 6, same as turnaround. We divided by 6, so we got at the 11.67 units for waiting time, for average waiting time, and then 18.67 units for average turnaround time. So why we divided by 6? Because we use 6 processor. Same here for the 8 processor. So for 8 processor, we divided by 8 because we use 8 processor, and we got for value of 21 units. And the average turnaround time, we got for value for the 30 units. Okay, here the 10 processor for It's the same as the eighth one and the previous one for 4 and 6. So we divided by 10. So why we divided by 10? Because we use 10 processes. So we equal to 32 units, and we got average turnaround time for 44 units. So here is the summary for the calculation. So to summarize, as the number processor increase, the average waiting and turnaround time increases so linearly in uniform burst time scenario, but exponentially when the burst time is vary. So FCFS, first come first serve algorithm, is a simple fair but become inefficient in diverse workloads due to the convoy effect. So our theoretical and simulations values constantly matches, so reinforcing the validity of our analysis. That's all for me.
Greetings to Dr. Pais and Dr. Aimi. My name is Divaharan, and I'm going to be presenting about the SJF, which is the shortest job first. So, in a very simple term, shortest job first is basically a CPU scheduling algorithm that actually picks the process with the shortest execution time to run next. So, for example, in a coffee shop, there's a line. So, in a coffee shop, there's a line, and the person who needs the least time to order, where they can think of their coffee on the spot, they go first. So the CPU, what it does in shortest job first, it chooses the process that will finish the quickest. So what happens in algorithm description of SGF is, it looks at all the waiting processes, no matter how many processes it is, then it finds with the shortest burst time. The shortest burst time means the fastest execution time. Then it runs that process to completion. Then it repeats until all the processes are done. So shortest job first basically, it brings forward the process which has the shortest burst time. So, for example, if three process, process A is 8 second, process B is 2 second, and process C is 5 second, it basically will run them in order of process B first, which needs 2 seconds only, process C, which needs 5 seconds only, and process A, which needs 8 seconds only. So when we say that SGF is a non-preemptive scheduling, what it means is once a process starts, it runs until completion. So preemptive means it can interrupt a running process if a shorter process arrives. But non-preemptive, which is what SGF is that once a process starts, it runs till completion. So this minimizes the average waiting time and is good for batch systems. But the thing is, it's hard to predict actual execution time. So it can cause long processes might never run because the short ones keep on arriving. So the long processes are basically starving for completion, and it's not practical for interactive systems. So over here we have the programming code for the SGF scheduling, and over here you can see that it's basically asking us to enter the number of processes, the burst time, and then sorting out the burst times. It will be sorting out first the burst time. So for each process, we can assign the burst time that we want to, and then what happens is it gives out the formula that it counts the waiting time of all the processes, it counts the average time of all the processes, it counts the turnaround time of each individual processes and the total turnaround time, and also the average turnaround time. So the following formulas, all it does is it gives the formula of how to count all those times that we require. So we're going to be moving on into the number of processes and the burst time that we have assigned. So for our first one, we're going to see looking. So we are comparing for each simulation for each number of processes with a same burst time and a different burst time. So for scenario, you can have the same burst time, where four of the processes have the exact same burst time. So when we actually assigned it, we can see that the average waiting time is 3 units, while the average turnaround time is 5 units. And the performance is that it's no optimization; it behaves just like FCFS, since all the burst times are equal. But for scenario B, where there's a different burst time, so we assign a burst time of 2, 4, 6, 8. So for each, so the process 1, 2, 3, 4, we assign a burst time of 2, 4, 6, 8. And you could see that it's ready. In a SJF is the shortest job first. It arranges the shortest to the longest. So the short jobs finish early first. So the waiting times go up to 0 to 6, 8, and 0 to 6, 12. And what happens is the average waiting time went up to 5 units, while the average turnaround time went up to 10 units. So what it does is actually this number demonstrates that the SGF strength, it's positive when it comes to minimizing delays for shorter processes. So it's more faster in that sense. So now next we're looking at the simulation result for six processes. So for the two scenarios, the exact two scenarios where once the scenario A has the same burst time, while scenario B has different burst time. So we, as usual, we put our execution order with the burst times that we assigned to it. So for example, for scenario A, the burst times that we put was actually for each one is 2 units, while for scenario B it's a different burst time. So it goes from 2, 4, 6, 8, 10, 12. And what happens is we can see that in scenario A, the average waiting time is 5 units, the average turnaround time is 7 units, and it behaves just like FCFS. So there's no any advantage given to SGF just because it has equal burst times. So there's no many much processes. But in scenario B, when there's a different burst time, what happens is it actually executes based on the shortest job first. So the short jobs are executed early. So let's say the waiting time it went up to 0 to 6, 12, 20, and 30, and the average waiting time is 11.67 units, while the average turnaround time is 18.67 unit. This once again shows that the SGF, when through the SGF optimization, that it can actually finish the shortest job first, but this also reveals that there's unfair delays for longer jobs. So longer jobs have to wait for a longer time since the shorter jobs are given priority. So the next one for eight processes, the same thing, two scenarios, scenario A and B. A has the same burst time, which is at 2. So the average waiting time or the average turnaround time, it SGF behaves just like the FCFS, and there's equal burst time. So it leads to none of the optimization benefit. But in scenario B, there's different burst time. We assign it to 2, 4, 6, 8, 10, 12, 14, 16 in that order. So just like the other SGF processes with different burst time, the short jobs are executed first. The long ones experience increasing delays. So the waiting time actually increase more and more for the subsequent process with the higher, um, with the longer burst time. So the performance is the SGF can reduce the average delay for short jobs, but as we increase the number of processes and we increase the burst time, it heavily penalizes the longer ones. Now, last but not least, for 10 processes, so it goes the same pattern. As you add 10 processes, if for the same burst time, it's going to be the same as the FCFS because there's no any um, priority given to any kind of all the jobs are considered the shortest job. So it is given, it goes in the same order of P1, P2, P3 until P8. And for the scenario B, where there's different burst time, it's the same thing. It's consider this as the most extreme case of SGF, where since we have 10 processes and we have longer burst time, so the waiting time increases much more higher and the turnaround time increases much more higher. So the SDF is good for shorter jobs, but when it comes to longer jobs, it causes a very big delay for it and it causes a longer time to actually execute those jobs. So when we actually compare the 4 to 10 processes and the time burst HCF, what we can say is that when you can have a look over here is that when there is the burst time is the same, it's like for example for the process count of 4, it's 3 seconds of average waiting time and 5 units of average turnaround time, and the performance impact is just the baseline. Okay, just imagine if you put that as a baseline. Now we start um, using different settings to see what is the performance impact. So for different burst times, the average wait time increases, the average turnaround time increases. Now it's 1.67 waiting, it's waiting even higher than that. It's taking a longer time. The same goes for every single time we use a different burst times for an increasing number of processes. The waiting time increases in a huge amounts because it is focusing on the shortest job first. So the longer jobs take a huge impact in this case. So let's say if there's more shorter jobs appearing again and again and again, the longer job will be starved, will be going through starvation and will not be taken priority in order to complete it. So the shorter job will give more priority to it.
Okay, hello everyone. My name is Konanda Sanaganasigaran, and my number metric is CN220005. Okay, now I'm going to talk about the process count, is average waiting time. Uh, the data analysis also. Okay, there are four types of processor in this table. For the same bus time for average waiting time is 3579, and the different bus time is 5, 11.67, 21, 33. So as you see in the graph, the average waiting time is directly proportional to the process count. So the graph shows average waiting time in SJF. Algorithm changes a number of processes increase, comparing scenarios with the same different bus times. When all the times are equal, SJFs behave like FCFS. So in contrast, the different bus time in graph shows a much steeper exponential rise in waiting time. So SJF prioritize shortest jobs, causing a longer ones to wait significantly, leading to an increase from 5.0 units for process. This illustrates while SJF is efficient for short jobs, it can cause high average waiting time and unfairness for longer jobs, especially the number of process, the bus time variability grow. Okay, same like the previous data. This one is the previous count versus the average turnaround time. So there's same like before this. They got four types of processors. The same bus time, average turnaround time is 5, 7, 9, 11. Then different bus time is average turnaround time 10, 18.67, 30, and 44. So the average turnaround time is directly proportional to the process count in this graph as well. Okay, this graph and table for average turnaround in SJF shows how turnaround time changes with the number of process and bus time variation. When all process have the same bus time, example like 2 units, turnaround time increases linearly and predictably from 5.0 units for process to 11.0 units. In contrast, when process have different bus time, SGF prioritize shorter jobs, causing longer process wait more. This results in a dramatic increase in the turnaround time from 10.0 units for process to 44.0 units 10 process due to cumulative delay experienced by longer jobs queued by many short ones. The data is highlighted that while SJF is efficient for small or uniform systems, it becomes less effective and unfair in larger. So more diverse workloads, as clearly shown in both in graph and table. Okay, this one same like before. The process count is the same bus time. So the graph shows a same bus time scenario. SJF shows a linear relationship between the number of process and the time matrix, average waiting time, average turnaround time, and the total execution time. Since all bus times are identical, example like 2 units, so SJF behaves like FCFS, first come first serve, with no prioritizations possible. As more processes are added, the average waiting time increases uniformly from 3.0 units to 9.0 units, while average turnaround time rises steadily from 5.0 to 11.0 units. Total execution time also increases proportionally as each process contributes a fixed CPU load. This consistent pattern demonstrates fairness and predictability under equal workloads and also shows that SGF provides no performance benefit over simpler algorithms like FCFS when all processes have the same bus time. Okay, this one process count versus different bus time. Okay, the graph and table shows different bus times, process count versus the time metrics, and SGF algorithm show how increasing the number of performance. As process count increases from 4 to 10, average waiting time rises from 5.0 to 33.0 units. The average turnaround time increases from 10.0 to 44.0 units due to longer process waiting behind many short ones. So the total execution time increases steadily with more process reflecting the sum of all bus time. So the data also includes an efficiency loss ratio, comparing performance the same bus time scenario. For example, the 10 process average waiting time in is 3.67, higher than the uniform bus case. This analysis highlights that while the SJF efficiently handles the shop jobs, it causes significant delays for longer ones as process count and bus, bus time variation grow, demonstrating the trade-off between efficiency and fairness in CPU scheduling. Okay, comparison with theoretical analysis calculation. Okay, for process, the bus time is 2, 4, 6, 8. And for, okay, as you see in the calculation, the total waiting time is 0 plus 2 plus 6 plus 12 equal to 20. And then average waiting time 20 over 4, which means the 4 processor equal to 5 units. Okay, average waiting time showing 5 units. As you see in the simulation result, in the corner at the bottom of the code, it will give 5 units also, same as is proof in the calculation. Okay, for the turnaround time, the formula is waiting time plus PT. Okay, turnaround time, total turnaround time is 2 plus 6 plus 12 plus 20 equal to 20, 40. So have to divide by the 4 process, which give 10 units. This proof in the simulation result at the bottom of the code will give, it will also show the 10 units average turnaround time also. Okay, for the 6 processor, the bus time shows 2, 4, 6, 8, 10, and 12. Okay, for the each processor, it will be plus by 2 also, same like before, the same as the 4 processor. Okay, the average waiting time. Okay, it's sum of the 0 plus 2 and 6 and 12 and 20 and 30. The 70 and then divided by the 6 processor will give 11.67. So same goes for average turnaround time. Have to plus 2 plus 6 plus 12 plus 20 plus 30 plus 42, 112 divided by the 6 process also, 18.67. 11.67 for the average waiting time and 18.67 for the turnaround time. uh, Same value as given in the 6 processor simulation result in the bottom of the code, so which means the calculation is proven correct. Okay, same like the 6 processor. For the 8 processor, the bus time is 2, 4, 6, 8, 10, 12, 14, 16. Okay, average waiting time have to calculate the value of the bus time. So altogether will be 168 divided by the 8 processor will given 21. So average turnaround time also same like before. Have to add the bus time also, 2 4 sorry 2 6 12 20 30 42 56 plus the 72 and divide by 8 processor. 240 divided by 8 will give 30. Okay, average waiting time for a given 21, average turnaround time will give 30. So this value you can find in the simulation result at the bottom of the code. It will show same like the calculations result also, which means the calculation is same as the theoretical analysis also. Same as before. 10 processor, the bus time is 2 until 20. Sum it that all together will be get 330 and divide by the 10 processor will get 33. So average turnaround time, sum the turnaround time 2 until 110 we get 440 and divide by the 10 processor we get 44. This prove that this answer is same as the simulation results as shown in the bottom of the code, which means our calculation is exactly correct to the simulation result also. Okay, summary of the calculation. Okay, theoretical analysis of the shortest job first SJF algorithm was concluded 468 and 10 process with increasing bus times. The results show that SJF consistently schedules. Results show that the ascending bus time order, resulting in predictable and turnaround times. For example, average waiting time increased from 5.0 units to 33.0 units, while the average turnaround time rose from 10.0 to 44.0 units. This finding confirms that SGF effectively minimize waiting waiting time for shorter process, but causes longer process to experience greater delays as systems grow. Theoretical values closely match simulation result, reinforcing SJF efficiency in small scale systems and revealing fairness limitations in larger, more diverse workloads.
So the thing is that you can see that when it comes to the summary of scheduling algorithms, so like we said, there's non-preemptive. Non-preemptive basically means once a process start, it runs till completion, and in execution order for FCFS, it comes based on arrival time. So first come first serve, whichever comes first, that process is executed. But for SJF, it's the shortest job with the shortest burst time. That's what's executed first. So for burst time knowledge for FCFS is not required a knowledge because it's basically executing based on the order of the processes. While for SGF it is required because based on that only we are actually executing the job. But the average waiting time for FCFS is much more higher, especially with long processes, because for FCFS it's going to come based on the first come first serve. But for SJF, it's much more lower, but it's because optimized for short processes. So for short processes, mean there won't be much delays, but for longer processes, there will be much delays. And for turnaround time, for FCF, it's mostly to moderate to high, while for SJF, it's lower in most scenarios if we have more shorter processes. And for starvation risk, for FCFS, it's quite low because no matter what, each process will be executed at one part. But for SGF, it's high because for long processes, they have to wait till the short processes are executed. And when it comes to fairness, SFS is quite high because the processes are treated equally. Each process are treated equally and they come in a first come, first serve order. While for SJF, it's quite low because longer jobs may staff due to their higher burst time. And it comes to efficiency, FCF is much more lower because let's say there is the second process which has a longer burst time than the third process, it would have to execute the second process first. So it'd be taking much more longer time compared to SJF because it goes based on the workload. So whatever workload which is lesser, it executes it first, only then it goes to the higher workload. And the best use case for both is FCF test is in simple, smaller workloads, while SGF in bad systems with a predictable burst times. That's where it's much more efficient to be used. So basically, when it comes to the graphical analysis, we can see that in FCFS and SJF, is that the average time comparison when we compare both of these is that when in a identical waiting time, identical burst times, the FCFS is not very different than the SJF, and they behave in in the same manner. However, in real world selection and a real world scenario, the SGF will perform better because it performs better because it selects the shortest job first. So it avoids delays caused by longer processes. And the graph that is portrayed over here shows that even though as the number of processes increases, the scheduling efficiency becomes more critical, while equal burst times shows that both algorithms are quite equal here, efficient wise. When it comes to different workloads, that means different burst time, SJF is more effective to minimize the waiting times for the processes.
To conclude our presentation, we analyzed two CPU scheduling algorithm FCFS and SJF using both theoretical and stimulation based methods. For FCFS is simple and fair. It runs process in the order they arrive. However, it often lead to longer waiting time when large tasks come first. On the other hand, SJF give better performance by running the shortest task first, which reduce average waiting and turnaround time. But it needs accurate and burst time prediction and may cause for longer jobs. For the SGF needs to know the job length in advance and may ignore long jobs. Stimulation with 4 to 10 processes showed both are similar when burst time are the same. SJF is better when burst time are different. Overall, use SJF for batch job with known times and use FCFS for system with unknown or changing job lengths. Main takeaway: choose based on what matters more, fairness or speed. That's all from us. Thank you.